Sorry for this delay with the start of our second talk. I'm glad to give a floor to Nikolai Vavilov, and his talk devoted to exceptionally involving polytopes, and the full details maybe he announced.
Okay. Thank you very much. Thank you, Nikolai. Actually, it is, as we know, the first conference without Volodya, and he would enjoy certainly these kind of things we are doing. So he's one of the persons who would be missing for this talk. Of course, another one who also died last year is Ernest Borisovich Winberg, who made a fantastic contribution to the study of exceptional polytopes in Lobachevsky spaces. But my talk will be mostly expository because actually it is based on our joint work with my diploma student, Viktor Migrin. So that's what I'm telling you today is part of his diploma. I will show you how the calculations look like. The subject is very classical. And as I said, the talk will be mostly expository. So in the first part, I will recall you the current status of the classification of semi-regular polytopes, solids, as you would call them, in the three-dimensional space. Then I will sketch you, just list basically, and give some hints on the tools we are using, because we can calculate with the exceptional polytopes essentially by hand in dimensions 7, 8, and 6, 7, and 8. Well, of course, also in dimension 5, but that's not interesting. In dimension 5, the preceding one is the demicube. Okay, so you just take half of the vertices of the 5-dimensional cube, and that's trivial, of course. But starting with dimension 6, it's not trivial. So I'll start with recalling you the status of the classification of the semi-regular polygons. So what are the regular polygons? The regular polygons are the polygons for which the symmetry group is transitive on flex, is transitive on vertices and edges that contain those vertices, and then two-dimensional faces that contain these edges, and so on, up to the facets, the faces of codimension 1. Okay, so that's a polytope, and as we all know, in dimension 3, there exists. In dimension 2 is sort of not interesting, but in dimension 3, regular polytopes. In dimension 3, there are 5, sorry, 3, 3, 4, 3, 3, 4, 5, 3, and 3, 5. And these are the tetrahedron, the octahedron, the cube octahedron, hexahedron, the dodecahedron, and the which one is the dodecahedron? Vitya. This is the icosahedron, and that's the dodecahedron, yes. And this, of course, is known since classical antiquity. But in the 19th century, Schläfli generalized classification of regular polytopes to all dimensions. And there, the strange thing happens. Okay, the thing that shows that they are very, very rigid. And so when you generalize this to higher dimensions, then eventually, starting with dimension 5, there are only 3 of them, which are the simplex, then the polytope, then, which doesn't have obvious name, well, it has too many actually. We used to call it hyperoctahedron. But in English, it's usually called cross polytope. Or orthoplex, or whatever. Well, it's in Coxeter notation, it's alpha n, this is beta n, and then, of course, there is one more, which is 3, 4, which is a hypercube. And these guys are in all dimensions. But what Schläfli discovered was the interesting thing, that something interesting happens in between. Well, of course, this is interesting enough already. Okay, this is boring for me. So mathematics that would look like that, for me, would be extremely boring, actually. Okay, because this is just a cone over the previous one. This is just the suspension over the previous one. And that's just the product. Okay, so there's nothing except for obvious constructions. Okay, so what Schläfli discovered is that apart from the 3 obvious ones, in dimension 4, there are 3 more. And these are exactly the 3 which are related to our talk. And these are the 3, 4, 3, the 5, 3, 3, and the 3, 3, 5. And these have symmetry type H4. And this one has symmetry type F4. Okay, and F4 and G4, H4 are exceptional. Exceptional Coxeter groups, well, what exceptional whatever. Exceptional reflection groups, of course, yes. And this is for the regular polytopes. What's a semi-regular polytope? Okay, oops. Let me maybe try to. Well, here, this is described, the situation with the. Is it the case? Am I confusing? Am I confusing 4 and, no, maybe yes. Maybe I should have put here 3, 4 and here 4, 3. I'm always confusing that. But okay. So, and these are the oops, no. Yeah, these are the 3 exceptional ones. Which has 24 facets, 600 facets, and 120 facets. And what are the semi-regular ones? And these are precisely the animals that we are studying. Okay, the semi-regular ones. Polytopes. Well, these are the polytopes which have 2 properties. First of all, the symmetry group should be transitive on vertices. Okay? All vertices should look the same. But that's not enough. So first, okay, transitive symmetry well, I will denote it by G, the symmetry group of the polytope. G is transitive on vertices. And second is that all facets, well, I recall you that facets are the faces of the highest dimension. All facets are regular. Okay, then we will make it the condition weaker. And of course, again, even if, and of course, for the time being, we only consider convex polytopes. Okay? And then, of course, as we all know, the classification of these guys in dimension 3 was given by Kepler at the beginning of the 17th century, the very, very first years of the 17th century. Kepler classified these guys in dimension 3, okay? Kepler, and this was Schläfli. Kepler classified these guys in dimension 3, and these guys in dimension 3 so are either regular or properly semi-regular, okay, which are called Archimedean solids. Or two series of the ones that are not interesting, prisms and anti-prisms. Okay, prisms and anti-prisms. Well, they're called Archimedean because people say that Archimedes classified these guys long ago, but his manuscript was lost. It was mentioned that he has discovered 13 bodies, 13 solids, but actually the first drawing comes from the early 17th century. Okay, but this is in dimension 3. What happens in dimensions 4 and higher? Okay, and this, the key person here was Gosset, Thorold Gosset, who was an English amateur. He was a lawyer, actually, not a mathematician. And he discovered and published in 1900, exactly, he published a list of 7 semi-regular polytopes in higher dimensions. 3 in dimension 4, 1 in dimensions 5, 6, 7, and 8. Okay, and the ones in dimensions 5, 6, 7, and 8, they are related to D5, E6, E7, and E8, which are famous as lattices or as root systems or whatever. Okay, and Коля, чего нету? Нету мела. Мела вот последний такой полу. He constructed these polytopes. They are remarkable. Well, actually, combinatorially, I'm speaking about geometric polytopes. So for me, polytopes are actually pictures, are actually configurations in Euclidean spaces. I'm speaking about Euclidean polytopes, not otherwise, not polytopes in Lobachevsky spaces, for instance. Okay, geometric polytopes, not combinatorial polytopes, because of course, as combinatorial structures, These guys were known before, well, except for the last one. This is called the, oh gosh, it's written in my text. In our text with Victor, the, yeah, right. The Klebsch polytope, the Schläfli polytope, the Hesse, and that's one, the Gosset. But collectively, one speaks of all of them as the Gosset polytopes because he has published them as a list and claimed that there are no further ones. Okay? Well, now we know there are no further ones, but that was established in 1991. Even in dimension 4, it was established in 1988. Actually, спасибо. Спасибо большое. Okay, actually, I could tell you that, well, this one has 27 vertices, that one has 56 vertices, and that one has 240 vertices. Okay, and there are no further ones, which are semi-regular. Well, you can ask, what happens if you remove one of these conditions, or weaken one of these conditions? Well, if you remove this condition, nothing happens. There are no, all polytopes in dimensions 5 and higher that are with regular facets. They are just the classical ones. The regular ones, the semi-regular ones, and prisms and anti-prisms, nothing more. But in dimension 4, if you remove this condition, you get just as by cutting, yes, just by cutting the 600 cell, you get this number of non-isomorphic polytopes with regular faces in dimension 4. So dimension 4 is really exceptional. It is really, really exceptional. Okay, but these, of course, are the most interesting ones. And actually, the next person to study them was Elte in 1918, I think, something like that. And he has rediscovered these guys. He was also not a professional mathematician, he was a school teacher. And he rediscovered these ones, but also he defined semi-regular polytopes inductively. Oh, thank you very much. Thank you. Thank you. He defined them inductively in terms of, so his semi-regular polytopes, the Elte polytopes, they could have semi-regular facets. Not regular facets, but semi-regular facets. And then, of course, here you have 3 other guys. Only that one of those is still the same 27 dual, and another one is 72. And here is 126. And of course, these numbers are reproduced here, but I'm not doing this on the blackboard. On the blackboard. These numbers are somewhere here, but anyway, I could give you the number of vertices of these guys. Yeah. So that's the number of vertices of the other guys. 500, so the numbers that you should put here is 576, and then these 2 numbers here. So this is what Elte discovered. Okay, since here there are experts in algebraic groups and representations, I will tell you what this means. These polytopes, you get them by circling one of the and nodes of the corresponding Dynkin diagram. So that's this one. The next one is this one, and this one is that one. For instance, and the same for
Just the while orbit of highest weight?
yes, just the highest weight. Yes, right. The highest weight, and you get the you take the Weyl orbit of the highest weight, and you take the convex hull. Okay, so and these guys are extremely interesting. Coxeter claimed in his book in 1948 that he has completely classified these guys, and he has completely described their faces of all dimensions and so on. But he also claimed that he classified these guys not just convex, but also the stellar ones, stellated ones, like the ones which were in dimension 3 classified by Kepler, which are not convex. But just 2 years ago, 2-3 years ago, Peter McMullen announced the following thing. And this tells you what happens with the, Peter McMullen actually announced that there are, even in dimension 4, there are 6 configurations missed by Coxeter in Coxeter's book. But dimension 4, as I said, is exceptional. And now what I'm going to tell you is that actually these exceptional configurations, they are so exceptional because they come from E8, because they come from the folding of E8 to F4, to H4. To H4. They come from the folding so that's the picture of E8, which is drawn in a slightly different fashion. Okay, and when you fold it, so you take the corresponding projection to dimension 4, you get something non-crystallographic. You get 5 here. So E8 falls to H4, H4 in dimension 4. Okay, and that's exactly what explains these exceptional things. Okay, so now, how you, if you switch on, you use the computer, you use it to record. If you could find on the internet something like publicity photo or publicity picture of E8. Well, I haven't thought of doing that. Yes. Yeah, can you do that for me? Thank you very much. Publicity photo for E8. So what people would do, people would try, of course, well, most humans are very bad at computations. Very, very bad at computations. Okay? Publicity photo of E8. You can look at, say, Garibaldi or Coxeter, or McMullen, or something like that. Just use it in conjunction, or constant. Use it in conjunction with some name. Garibaldi, E8, the very exceptional group. The most exceptional group. Right, there, here it is, yes, right. That's what you see, and that's the picture of the smallest guy. That's the picture of this. What can you do with this picture? Can you calculate, can you compute with this? Oh, it's very beautiful, of course. But that's the picture of E8, of this E8 polytope projected on the two-dimensional space. Okay, that's the so-called Coxeter projection. You take the Coxeter plane. Okay, the smallest eigenvalue of the Coxeter element. What Macmillan used when he classified, Macmillan last year, 2020, published a book where he corrected Coxeter results, and that's the first complete classification of semi-regular polytopes in all dimensions. Okay, including the non-convex ones. The convex ones were classified in 1991. It was proven that this list is complete, but much, much later than claimed. Okay, but usually people use this kind of picture. Macmillan uses a completely different kind of picture. He also takes projections to the two-dimensional space. Okay, but he takes projections. Here they tried, actually here the there are two kinds of projections. That's one. Another one is when the central vertex represents, here are 8 times 30, okay, the circles. But there is another projection when you have 2 points identified in the center. Macmillan uses different kind of projections. He uses projections where some vertices in the two-dimensional picture represent vertices of the big guy, and some other vertices are projections of higher dimensional faces, and some of them sometimes are projections of the whole facet. Okay, but if you have several such pictures in front of you, with some mental discipline and a lot of exercise, you can compute with them, and the whole book by Macmillan is done like that. He looks simultaneously at several such projections, and he reconstructs mentally the whole picture of these guys, which is amazing. So what we do here, this was actually based on, initially I proposed this to the school children in Sirius, but somehow it turned out not to be non-practical to explain within, say, a few weeks what root systems are to the level sufficient to actually calculate something. And then when last year Victor asked me for a problem for his diploma, we discussed, and I said, well, this is still open. He said, why? And he wanted to try. So what we are using instead of these pictures, can we return to the, yes, to this paper. Yeah, right. That's the picture. That's the picture. Yeah. No. Well, that's the picture. Yes, but I would like to show in the other file the three of them.
Together.
Well, no.
Oh, yeah.
This one. Mm-hmm. Thank you very much. Yep. Yeah, right. We are using instead of these publicity photos, which are useless, and instead of Macmillan diagrams, which are very useful, but which require a mind like his, you know, and a lot of exercise even then, okay, we use these projections, which are not faithful projections, which rather just depict combinatorial structure. And these pictures we used a lot for a number of years. For a few decades, we used them in representation theory of algebraic groups, and then in the theory of homogeneous spaces, and so in calculating the algebraic groups, and so on and so forth. So if you count the vertices of this guy, these are the 27 vertices, and that's these 27. That's the faithful picture of the Schläfli polytope if you know what stands behind. Okay, so you need some extra information. You need some extra information. I have to sort of observe how much time do I have. Koля, how much more time do I have? Because that I have to decide how many details I have to tell. We started a bit later, but that doesn't matter.
At least 20 minutes.
Okay, good. That's enough. So, well, of course, apart from these pictures, we use some information that we have, that we know about root systems. Okay, what do we know about root systems? For instance, we know, well, root systems, as everyone knows, are pictures like that. Here I draw my favorite one. Well, actually, it's not. My favorite one is E6, but I cannot draw it. That's the picture of G2, in dimension 2. E6 is in dimension 6. I cannot draw it. Well, I can, but it will look like that. That's half of E8. And so for E6, you just have to cut this picture before the first occurrence of 7. For E7, you have to cut this picture before the first occurrence of 8. And for E6, before the first occurrence of 7. So that's the picture of the positive root of half of the vectors of E6. So we use pictures like that. That's the picture of E8. That's half of the vertices of this polytope. And E7 was somewhere in between. So we use these kind of tools, which are maybe not as beautiful, but for me they are, as the publicity photos. Okay, but for me they are much more informative than the McMullen's projections. Because here in these pictures, all vertices are vertices. So all 27 vertices, of the 6-dimensional semi-regular polytope, the Schläfli polytope, are still different vertices here. And the edges, so what's the difference? The publicity picture depicts all the edges of the polytope. All the edges of the polytope. And the edges of the polytope, they have a color. And that color is called the positive root. And here, we erase all of these edges apart from the ones in 6 chosen directions, which are called the fundamental roots. So you take 6 linearly independent dimensions, okay, and then you start applying just reflections, not with respect to all roots, but with respect to these fundamental roots. But since the fundamental roots generate the whole root system, their corresponding reflections generate the whole Weyl group. And all vertices are eventually obtained just by the fundamental reflections. Okay, so you can pass from the top thing to any one of them by a sequence of the fundamental reflections. And since all the vertices look alike, okay, the Weyl group is transitive. You can just look at one of them and look at what happens in its neighborhood. And by looking at that, you immediately notice that, well, it is contained, that the 2-dimensional face corresponds to 1, 3 is a triangle, is A2, that the 3-dimensional face is a you know, is a tetrahedron, 1, 3, 4, 4 vertices, tetrahedron. Okay, and then something strange happened, because when you look at the 4-dimensional vertices, there are 2 of them. After 4, you can go by 2, and then you cannot proceed. Or you can go by 5, and then you can proceed. So this means that you get 2 types of 4-dimensional did I say 4-dimensional faces, and all of them are, of course, 5 simplices, 4-dimensional simplices with 5 vertices, 4 simplices. But they are of 2 types. Why are they of 2 types? Because when you proceed eventually, you discover 2 pictures. You see one is like that, and another one is like that. Okay, and this is D5 and A5. And this corresponds exactly to the fact that this polytope has 2 facets of the highest dimension. 2 types of facets. One are 5 simplices, and another one are the 5 octahedron. But of course, in dimension 5, the octahedron is the demicube, yes, half of the cube. It's exceptional dimension again. Okay, dimension 5 is also exceptional. And then, of course, the 2 types of 4 simplices are explained by the fact that the 4 simplices can be the intersections of either a face of this type with a face of that type, or can be the common face of 2 facets of this type, of the first type. So you see the whole combinatorial structures from these pictures. We can reproduce the whole combinatorial structure using just the following 2 things. We know the root subsystems, and we know the conjugacy classes of the Weyl group. And of course, that was classically established by root subsystems by Borel, de Siebenthal, and Dynkin, and the conjugacy classes of the Weyl group by Frame, Carter, and then other people later, Stikolchik and Geek, Pfeiffer. Other people made further simplifications. We now made yet another one. But anyway, that's classical foundational material. We are not using any advanced computations. So as a first step, we reproduced the computations of types of facets, types, numbers of facets, and adjacency, which were performed in 1991 and 1992 by Conway and Sloan, and then by Moody and Patera. Okay, but then, our main new result, but we are working on other things, and I think we can explain much more. Our main new result is as follows. And here it is interesting to show, yes, that's the picture of E7. That's the picture of E7, that's the picture of this polytope, of the Hesse polytope. Okay, and we looked at the colorings of these polytopes, at the colorings of the vertices or facets of these polytopes. You know, this is how it all started. I proposed this problem to the school children in series, how many essentially different colorings there are of such a polytope, say with 2 colors, with 3 colors, and so on. And of course, the method to calculate these numbers is well known. It is called the Poya-Redfield enumeration theory. And but that requires to calculate some polynomials, the cycle indices of the actions. Okay, and of course, it's not a secret that you can do this on computer, just by brute force. Okay, but this was calculated by hand. And I will show you how, by Victor. And this, yes, these numbers here, they just to give you some idea of what polynomial growth is, because we all speak about exponential growth, but polynomial growth also can be very, very fast, you know. That depends on your polynomial, of course. So here, the first number shows you that just the number of colorings of this guy, of the root polytope of type E7, of its facets in 2 colors. It's big, isn't it? So I thought you would get an answer. Well, but it's still smaller than 2 to the power 54, if you have some doubts. Yeah. I know that I couldn't believe that. When I've seen this number, I couldn't believe it. Because I would expect something, an answer of the same type as when you ask, how many essentially different ways to color the faces of a dodecahedron you have, or something like that. No, something between dimensions 3 and 6 in this case, something happens. By the way, of course, dodecahedron is just the, well, icosahedodecahedron. It's just the twisting of E6. So if you remove these nodes, you twist E6, you fold E6 to H3. You just remove these nodes. So actually, it is related to the dodecahedron. But somehow, for some reason, it's much, much larger in dimension 6. And the second number is when you plug in 3 in there, when you plug 3 colors there. And that's called polynomial growth, you know. Okay, and that's just for the simplest case. Because this guy is semi-regular in the sense of Elte, not of Gosset, in the sense that it has semi-regular facets. It has 20 semi-regular facets, 27 semi-regular facets of one kind, and 27 positive spin for D5 and 27 negative spin for half spin for D5. Okay, and when so you look at those and color those, you get this kind of numbers. And now I would like to show how this was done, so that you would be amazed. It was not done by, it was done without computers. And now you can imagine what we can do now by using computers and using this information that we used to do this by hand. So that's the whole calculation to get these numbers that I've shown you. It is all here. It is for all representatives of all conjugacy classes, which are here described by root subsystem. Well, apart from the 2 cuspidal ones, well, there are more cuspidal ones, apart from the ones that do not correspond to the root subsystems that are new for E6. Okay, and just, so these are the 3 classes, these are the other 3 classes, and the 4th starts. You just look at the vertices and and look where it goes under the fundamental reflections that generate this subsystem. And that's it. And Victor just colors. If you see the vertices are colored, just to distinguish the orbits, he uses different colors. That's it. And so these are the three further ones. Okay, and the interesting thing, that's Carter diagram with cycles. That's a very interesting thing. That corresponds to the classes. They are not Coxeter classes of subsystems. They are new for this case. This one is new for D4, but of course it survives in E6. Okay, and there are, at some point something interesting happens. You see, that's the whole calculation. That's how we calculate. Something interesting happens for this system. For this conjugacy class. That's an interesting class. That's the cuspidal class discovered by Carter. This class gives you 3 9 cycles. And of course, we all know from school that 9 cannot be the order of the rotation axis of a crystal. Well, it can be. It cannot be a rotation of a crystal in dimensions 3 or 4. But it very much can be a rotation axis of a crystal in dimension 6. And it's here. Already you see this. That's the crystal that has a rotation axis of order 9. Okay? Of course, already in dimension 4, you have a rotation of order 5. And this is what people call quasi-crystals. Quasi-crystals are projections of the 4-dimensional things in our 3-dimensional world. And that's it. And here you have an axis of order 9. And that's the whole calculation. You just add the, and that's the last, in a sense, most difficult cuspidal class, which corresponds, well, the 6 roots are linearly independent, but they form cycles. Okay, they are not Dynkin diagram of something smaller. And you just add these guys, and you get this polynomial. But of course, then to plug in 2 or 3 there, you need a computer. This we cannot do by hand. And what Victor done lately is that he has done the same computation for E7. I have part of it in my computer, but I haven't sent it to you. But he has done the same calculation by hand for E7. So we can compute by hand in these guys. But actually, for the rest, we are going to use computers. And then we will come up with similar polynomials, but which maybe will be too large to show for you. Because if you look at E8, it has about 200, more than 200, 212, I think, conjugacy classes, something like that, which is already, to do by hand is a bit boring. Okay, but otherwise, I think it was useful, a useful exercise for us that we can, just like that, repeat all the results that are in the published literature and can do other things with these pictures for the small examples. But then, of course, we are going to try to apply this also to the larger ones, and there are further polytopes with these types of symmetry which are not semi-regular, which have weaker regularity, uniformity conditions. But that's for the next talks, maybe. There is much more behind, but I do not have time now. Thank you.
Okay, thank you very much. A very informative and impressive talk, and it is hard, I hardly believe that a lot of such computations was made by hand
Here.
in a few days, actually.
2 evenings. The computation for E6 was 2 evenings. Well, it was 1 evening to explain how to do that and 2 evenings to compute.
And we'll wait your computation. actually a lot of detail. The abstract, which you can see through the BCA web page, consists of 23 pages.
Yes.
And you can find in this, and it is only abstract, but I've
It's just,
I'm
yes,
told
of course.
that, we will publish full proceedings, maybe devoted to Vladimir Gert, and we will be glad if you present.
I forgot to.
more detailed
I
paper.
forgot to tell you the most impressive thing. The most impressive thing is what the Dynkin diagrams are of the. That's the Dynkin diagram for. Sorry. Well, I tried to draw the three squares. This I'm telling to Vladimir, and he studied the nets on a torus and discovered in one of these previous conferences that this net has an exceptional behavior. Well, it has an exceptional behavior. Of course, I immediately noticed that this is related to F4. But actually, if you read the paper by Dynkin and Minchenko, they discover that this is the enhanced Dynkin diagram of type E8. And so the exceptional symmetries. This picture, in a sense, is much more complex than the rest because it inherits the symmetry from
Begin to remember.
of the 8-dimensional space.
Okay, thank you. Other questions? Maybe.
So this picture describes Brillouin order, right?
Well, Brillouin order, the adjacency of Brillouin cells, well, this is, in the case of microwave representations, it doesn't matter.
Well,
In the case of,
my question is precisely doesn't matter because you also have pericentric subdivision of your polytope and it's simplish complex and so it's also some partial ordered set.
yes, but for these cases, it doesn't matter because this picture represents faithfully the, well, for E8, that's part of the problem with manual calculations, that you have at least to introduce the faces that correspond to the maximal root. At least. You cannot do this with the root reflections because the root reflections, the fundamental root reflections, will bring you inside, will bring you to zero, which is not the, whereas you can go, on the surface of the polytope. So yes, of course, for E8, you use a slightly different picture from this one. Yeah. You are right.